Curves in industrial design. B-spline control polygon and B-spline polar. Consider a cubic B-spline composed of just two Bezier pieces, the first C1 in red defined on U0, U1, and the second C2 in green defined on U1, U2. If C1 with 3 entries denotes the polar form of the first Bezier piece, and C2 with 3 entries denotes the polar form of the second Bezier piece, the continuity condition at the joint of the B-spline curve is equivalent to both polar forms C1 and C2 being equal when evaluated at U1 3 times. The smoothness condition of the B-spline curve, that means the B-spline curve is C1 at the joint, is equivalent to both polar forms being equal when evaluated at U1 twice and U0 once, or when evaluated at U1 twice and U2 once. The continuity of the curvature of the B-spline curve, that means the B-spline curve is C2 at the joint, is equivalent to both polar forms being equal when evaluated at U0, U1, U2. The B-spline control polygon of a cubic B-spline curve can be given in terms of the polar forms of its two Bezier components. Let C1 be the first Bezier piece parameterized by U0, U1, and C2 the second Bezier piece parameterized by U1, U2. The B-spline control polygon is denoted by D0, D1, D2, D3, D4, and here we can see the B-spline control polygon and the B-spline curve, with its two Bezier pieces, the first one in red and the second one in green. We are going to relate the polar forms of these two Bezier pieces with the B-spline control polygon. So the first control vertex of the B-spline control polygon is the polar form of the first Bezier piece evaluated at U0 3 times, this vertex here. The second control vertex of the B-spline control polygon is the polar form of the first Bezier piece when evaluated at U0 twice and U1 once, this vertex here. The third control vertex of the B-spline control polygon is the polar form of the first Bezier piece when evaluated at U0, U1, U2, this vertex here. Or, because of the C2 condition, is the polar form of the second Bezier piece when evaluated at U0, U1, U2. These both are equal, and is equal to this vertex. The fourth control vertex of the B-spline control polygon is equal to the polar form of the second Bezier piece when evaluated at U1 once, U2 twice, this vertex here. And finally, the last control vertex of the B-spline control polygon is equal to the polar form of the second Bezier piece when evaluated at U2 3 times, this vertex here. So because of this C2 condition gives us a compatibility condition between the two polar forms and allows us to represent with a unique notation these polar forms. The notation we will use is C in orange, and we will draw the B-spline curve also in orange. So we will denote by C the polar form of the Bezier pieces, each corresponding to the right vertex. And for these two, the third vertex, this C corresponds either to the first polar form, the polar form of the first Bezier piece, or to the polar form of the second Bezier piece. So, if D0, D1, D2, D3, D4 is the B-spline control polygon of the cubic B-spline curve C composed of two Bezier pieces, the control polygon is related to the polar form of the B-spline curve as we mentioned before, and from it we can extract the knot vector. So, D0 is the polar form of the B-spline curve evaluated at U0 3 times, and it gives us that the first 3 entries of the knot vector are U0. For D1, we remove one of the U0s and add U1 at the end. So now that adds a new entry in the knot vector. And we keep going in this way. For D2, we add U2. For D3, we add another U2. And finally, for D4, another U2. Notice that the end knots of this knot vector have only multiplicity 3 instead of multiplicity 4 as in the knot vector that generates the basis functions. In general, If we consider a cubic B-spline curve C composed now by S Bezier pieces, the first piece C1 parameterized by U0, U1, the second piece C2 parameterized by U1, U2, the third one C3 parameterized by U2, U3, and so on, the joint of the Bezier piece Cj with the Bezier piece Cj plus 1 can be written as the polar form of the Bezier piece Cj evaluated at uj minus 1, uj plus 1, and it is equal to the polar form of the piece Cj plus 1 evaluated at the same entries. This equality is due to the C2 condition of the B-spline curve. So because of this C2 condition, this compatibility condition, we can write it as the polar form unified for the B-spline curve. And this is equal to the control vertex of the B-spline control polygon dj plus 1. So as we did before, from the control polygon of the B-spline curve expressed in terms of the polar form, can we extract the knot vector. So D0 is the first control vertex of the B-spline control polygon and is equal to the polar form of the B-spline curve evaluated at U0 3 times. So that gives the first 3 entries to be U0. As we advance, we add new entries in the knot vector. Now, U1 for D1, U2 for D2, U3 for D3, and so on. So we've seen there are 2 knot vectors that can be associated with the B-spline curve. The knot vector that relates the control polygon of the B-spline curve with its polar form, or blossom, the one we've just seen, and the knot vector that generates the B-spline basis functions via the Cox-de-Boer formula we've seen in previous videos. Both knot vectors are the same except for the multiplicities of the end knots. For a cubic B-spline curve, the end knots of the polar knot vector have multiplicity 3. The end knots of the knot vector used in the Cox-de-Boer formula to generate the basis functions have multiplicity 4, but otherwise those 2 knot vectors are the same.